Good afternoon, everyone. Thanks for staying. So my name is Matthew Branch. I'm the product manager at a company called Prophotonics. Prophotonics is one of the companies under the exhibitors brand. Today's talk is novel infrared multispectral imaging techniques. And I'll take you through a few items first. We'll have a look at some of the camera technologies that have been, have come about in recent years and how they've improved. Some LED technologies as well and how they've contributed to improved efficiencies. Before we'll have a quick look at chip-on-board LED technology. Now it's that technology or that format of LED that we're using in our Cobra line light product. And it's this Cobra line light product that is going to be demonstrated in a few of the case studies at the end. I will go through a few methods of image acquisition techniques in multispectral imaging as well. So, cameras are improving every year, and certainly some of the things that we're seeing at the moment are more compact designs, for example. So there is a company that is creating an 8K line scan image using two independent 4K linear arrays that are slightly offset from each other. And the question is why? Well, that basically reduces the footprint or the overall size of the product by as much as 45%. So things are getting smaller. There are faster transmission rates, of course. So Coax Express 2 and Camera Link HS, they're able to achieve speeds of 800 to 80 to 100 gigabits per second. There's some innovative designs out there. One company, for example, or quite a few companies, have multi-sensor, multi-array systems within one camera. So now we can capture one image from one optical axis that is covering different parts of the spectrum. It could be the visible spectrum, the RGB image, as well as this shortwave infrared spectrum as well, using in-gas sensors. And then, of course, things are getting more intelligent as well. So there are many cameras now that have onboard processing, and this is creating real-time decisions on board the camera, and it's minimizing the need for any expensive off-system analysis. And it's specifically important or useful in the areas of hyperspectral imaging when your data sets are so large. In addition to the camera technologies improving in recent years, there are still improvements in LED technologies. So for example, there's some very interesting novel sort of device heterostructures within the LEDs themselves. So one example is a distributed Bragg reflector. These are particularly useful in your white LEDs, for example. And what those heterostructures are doing is they're basically recycling some of the LED wavelength or the blue wavelength that is exciting the phosphors. So if you're recycling it, you're generating more output. Surface texturing, there are some novel surface texturing techniques as well, and specifically useful in the gallium nitride based LEDs. They were seeing a 30 to 40% improvements in efficiencies, and this is because with the surface texturing going on, you're reducing the amount of internal reflections, and thereby improving your extraction efficiencies. Overall, your internal quantum efficiencies and your external quantum efficiencies are still improving, especially in the near infrared region. Your internal quantum efficiencies are reaching 60 to 70% in some cases. And obviously, applications drive demand, and demand affects pricing. So we're still seeing reductions in cost and greater availability of LEDs. We're seeing this specifically in the SWIR wavelengths as well, but this talk is more about the visible and the near infrared. So LEDs come in different form factors. We're not going to go into a lot of detail here. Essentially, your S&D devices are the most prevalent in the likes of general lighting, but we're particularly interested in the COB, the chip-on-board device. So here we're taking the naked die itself, and we're generating the wire bonds to them, and we're creating devices or lighting solutions using this chip-on-board device. The reason why we do that is that it's very useful for high lumen output applications. You can cram a lot more of source within a surface area, within a two-dimensional area. So there's a few examples of some of the sources or actual lighting solutions we've designed. To take you to the top right-hand side, you can compare the number of different LED devices you can fit in a 10 by 10 millimeter array. So if you take your old-fashioned T-pack, for example, you might be able to fit 9 of them in that 10 by 10 area for a very low-powered device. If you switch that to a surface mount type LED, well, you can jam a few more of those in there as well. But with the chip on board device, you can fit so many more of these devices into that same square area. And that's really what we're trying to focus on over here. With a more compact source, you get a higher output, and certainly when you're starting to combine wavelengths within that source, you can improve your spectral uniformity as well. So a few examples of the images at the bottom that you see there. On the bottom left-hand side is one of our UV curing solutions. So there we have a 77 millimeter sort of wide module, and in that module have 200 of these chip-on-board LEDs. So that's a sort of a density of about 20 LEDs per square centimeter. The center image that you see there is a dental imaging tool. The diameter of that array is only 12.5 millimeters, and we can fit 192 LEDs in that solution. And on the bottom right-hand side, you can see the background image of the 10-cent coin there, and you can see the device on the bottom right. So this is a 10 wavelength multispectral device. Each one of those wavelengths are individually controlled. So this chip-on-board advantage we're applying to our line light solution. This is the Cobra line light. It's a multispectral and a hyperspectral solution. And it's got the usual configurability that you would associate with a line light. It can come in a variety of lengths, up to 6 meters, for example. It has interchangeable optics. It has interchangeable diffusers. But the most important thing about this for our purposes today is the fact that it can control independently up to 12 different wavelengths for each one of the 100 millimeter modules. Now those 12 wavelengths you can configure into one of 4 different strobe groups as well, which I'll show you in one of the case studies later. You can then assign certain wavelengths to certain strobe groups, and you can sequentially strobe those. Then it's controlled via Ethernet, and on the bottom right hand side you see the GUI, the graphical user interface, that allows you to control modules as well as wavelengths, etc. Now there's a few methods of color acquisition from a line scan approach or the push broom approach. One such method is the sort of trilinear or quadlinear approach. What you're doing here is you're taking 3 separate linear arrays and you're imaging or focusing them on separate sensors, line sensors, and each one of these line sensors are typically covered by a polymer filter. Those filters they don't really have a sharp cutoff in terms of the transmission curve, so you do tend to have a bit of color bleed when it comes to the different filters. So despite that drawback, it's a very fast approach to acquiring an image. It's a very cost-effective approach to acquiring an image as well, and a typical application, for example, is print inspection. On the middle image, you can see a different approach, prism technology. So here you're taking one line from your target, and you're splitting that through the use of a prism onto separate sensors. And those sensors typically use dichroic filters, and they have a much sharper cutoff in terms of the transmission curve. So you don't have this issue of a bit of color bleed. It's a much more sort of it's a higher degree of color purity in those solutions. It is a slightly more expensive solution, but it maintains your resolution as well. And lastly, quite important as well, is the switching source. So there's no need sometimes to go with a hyperspectral or a multi-sensor camera. You can just go with a monochrome camera, and you can switch the actual source itself. So certainly in the likes of the Cobra, which has you can have strobe speeds of in excess of 100 kilohertz. You can independently switch a red, green, a blue, and a near infrared, for example, and you can generate a composite image in that fashion. So moving on to the case studies, this particular case study, the end user, we gave them a solution and we added value to their solution through the particular wavelength choice that we chose for them and the fact that we're using this chip-on-board technology. This is in the area of seal inspection in the food industry. In the food industry, they create a thermal seal on the packaging, and that seal needs to be inspected for integrity, and is typically done using thermal imaging. And it needs to be done as close to the actual thermal seal process itself, whilst that seal is still warm. The problem is all that imaging needs to be contained within this hot zone. It wasn't working for the end user, and they wanted to switch to a different method of inspecting that seal. They considered the X-ray imaging, but that was sort of cost and safety prohibitive, so they wanted to go to a SWIR-based system. Now, the solution we provided them in the end for the full 700mm web width was in a backlighting configuration, and it was through the use of the chip on board that we were able to get the amount of intensity that they required and the diffusion and uniformity that they required for it to work for them. And in their own words, it was the best lights they've ever tested. But the real benefit to them was the fact that they were able to remove this inspection zone out of this hot zone, and they had greater flexibility in terms of their production line. The second case study is in the area of food inspection, or the food industry again. This customer was, so they had a very large estate in which they were distributing food, and each of the pallets that were used or loaded with food had to go through a cleaning cycle. And they were visibly inspecting the cleaning, the pallets for defects and alignment and so on, but they were not inspecting it for organic contaminant. And the means for inspecting for organic contamination is to use some of the SWIR wavelengths. They didn't have a solution at the time for the SWIR, and they needed to have a solution that could work at very long working distances, 300mm working distance, and it needed to be very easily rolled out across their entire estate. And obviously they were looking for reliability, and it was a very dusty environment. So it was a multispectral SWIR solution we supplied to them. In fact, just two wavelengths this time. The one wavelength that was chosen was as a sort of a contrast, so it wasn't being absorbed by any water in the system. And the other wavelength obviously was the 1450 nanometer wavelength, which some of you may know water absorbs. So there's a very large absorption peak at 1450. So by using these two wavelengths, they were able to be differentiate between organic and inorganic. So whenever the pallet would go through the inspection cycle, if it detected an organic contaminant, it would go through another cleaning cycle. So in the end, we did some modifications to their firmware as well that allowed them to have a soft start in their process, and we incorporated a dust shield as well because of the dusty environment. In the end, it was rolled out across the entire estate. Yep, sorry. The third case study, again, is also in food sorting, so in the food industry. Here we had an end user that they actually did have an LED solution at the time, but it wasn't working for them. So this LED solution, which I'll show you in a moment, basically they were doing nut sorting. They were doing some plastics inspection as well, and some grain sorting, but the majority of their sorting was nuts. And they were using RGB lighting, near-infrared lighting, and SWIR lighting at the same time. This was their original setup. They had a gravity-fed feed, and all the nuts were falling down through a chute, and they had imaging using from both sides of the gravity chute, top and bottom. And each one of those sources that you see on those four different axes, there were 3 individual line arrays. One had an RGB linear array of LEDs, one had a near-infrared linear array of LEDs, and the third linear array was for the SWIR solution. Now, they were limited in terms of their sort speed because they just couldn't increase the intensity of their SWIR wavelengths in particular, and they needed to increase the power there. But the problem is they couldn't just add more LEDs, they didn't have enough space. So they came to us for a solution, and there were various strobe constraints and cost constraints that they had. But in the end, we were able to combine each one of those linear arrays, the RGB, the near-infrared, and the SWIR linear array into one single linear array of our Cobra line light. So we combined, essentially reduced their complexity by 2/3, from three solutions to one. At the same time, we were able to maintain the original strobe conditions. So the RGB, for example, was operated in CW mode, but on the same linear array of LEDs, we were able to independently strobe the near-infrared and the SWIR infrared LEDs. All right. So overall, we simplified the system significantly. This is both related to the setup times as well as their actual alignment times and their complexity of their materials. For example, they did have 24 cables and connectors going to each one of these lighting solutions, and that was reduced to 8. They had 4 PCBs, and that was reduced to 1. So overall, a faster sorting speed with higher, more intense SWIR solution, an increased throughput, and overall a more simpler system to manufacture. So to summarize, 3 case studies explored. And through the use of the chip-on-board solution, the power and the uniformity of that, we were able to give value to a seal inspection system. In the second case study, it was the wavelength configurability, the choice of wavelengths that we offered, and obviously its ease of use and installation across the entire estate. And the third solution of nut sorting, we were able to configure 3 different line light solutions into one. So it's the power and the uniformity of the Cobra multispec, and the fact that we can configure each one of those strobe channels that added value to that end user. So that's it. Thanks for your time. I'll take some questions.
You showed the case study, I think it was the third one earlier, and in the setup, I was just curious, don't you have the issue that you then take images from both sides and have the camera on the other side? Oh, sorry.
Sorry, yeah.
Are you able to hear me? Okay. So in that specific setup, because we were looking into something similar, don't you have the issue that you take images of the camera of the other side?
So the camera was, there were you're imaging from both sides, so you don't get any shadows from one side. If you're imaging from just one side, you end up getting shadows on the other side. So you typically have lighting on both sides of the camera, and that prevents shadowing. So it would be one camera, multi-sensor camera in the middle, imaging from both sides, and then the same another camera on the other side and imaging from both sides.
Okay, so
yeah.
My question is, are you able to avoid a thermal camera if you are working with this lighting?
I think I heard thermal.
Yeah, like, are you able to avoid using a thermal camera when you're lighting with this near infrared or? Correct.
For the seal inspection system, thermal cameras are normally used to look at the seal, but you have to do that whilst the seal is still warm. But in the SWIR system, you can actually use 14, 15 nanometer wavelengths, and it would be able to detect whether or not there's any contamination in that seal that's preventing a proper seal. So you're using the actual absorption of water as an indication of whether or not the seal is good or not. And you don't need any thermals. Yeah.